I'm Conor Houghton, and this is Lecture 2 in the Information Theory section of our unit, Information Processing and the Brain. To recap stuff from the last lecture, this is Shannon's entropy here. So we have some sample space, x1 to xn are the possible outcomes. Each of them has some probability, and then h of x, Shannon's entropy, is equal to minus the probability of xi by the log of the probability of xi. We're using the notation here where you have p sub x, and that's going to be useful when we have more than one distribution we're dealing with, but as a shorthand we often leave it out, sometimes while talking, sometimes even when writing. It's log to the base 2, the entropy is being measured in bits. You could have different logs, but changing between them is trivial because it's just a matter of dividing across by log to the base 2 or whatever you want the new base to be. It looks like there might be a problem with p, log to the base 2p, not being defined if p is equal to 0. But for the purpose of this definition, p log to the base 2 of p is taken to be equal to 0. And that makes complete sense because using L'Hopital's rule, you can see that the limit as p goes to 0 of p log to the base 2 of p is 0. So Shannon's entropy, we should first of all rewrite it or see that it can be rewritten as an expectation value. I've used two notations to take the expectation value here. One, the Dirac notation with the angle brackets at the far right, and then in the middle, just the big E. I'm setting this up because people often use one or the other or change between the two. Either way, we can see that Shannon's entropy is a sum of the log of the probabilities weighted by the probabilities. In other words, it's an expected value. And interestingly, it's an expected value that can always be calculated. In fact, that's one of the nice properties of Shannon's entropy. I'll enlarge it in a second, but we should notice, and we will learn in this lecture, hopefully, that Shannon's entropy has lots of nice properties. We'll learn some of them in this lecture. As an aside, being easy to estimate isn't one of them. So to estimate Shannon's entropy from some sample data, well, it's an expectation value. And what you do then usually is you sample some of the data and work out the required function that it's an expectation value of. But here you actually need the probability. When you're sampling the data, you need to sample enough data, not just to be able to estimate the expected value of something, but to also estimate the thing that you're estimating the expectation value of. You need not just lots of values of x, but to actually have enough values to be able to work out or to estimate p of x. That's an aside, but one that we'll return to later when we're looking at how to estimate Shannon's entropy for neuronal data. For now, I want to note that you can always calculate Shannon's entropy for any probability space. There are, obviously the most commonly calculated expected value is, when we think of expected values, one of the first examples that we think of is the mean, the expected value of x itself. So the expected value of x is the sum of the p of x multiplied by xi, summed over all possibilities xi. But this only works if xi are in a vector space, because we have to sum them. If you were looking at the expected fruit that you or vegetable that you get, if you went into a fruit and veg shop and picked vegetables and fruit at random from the shelves, well, you might be able to work out, a quarter of the time maybe you get an apple, and an eighth of the time a banana, etc. But that doesn't mean that you could work out the expected fruit, because 0.25 times an apple plus 0.125 times a banana is nonsense. Shannon's entropy doesn't have that problem, because if you have a probability space, then there is a p of xi for each of the xi's. So the thing that goes into the formula, into the expected value, the log of p of x, is something that must necessarily exist. And you can perform sums in it perfectly well. If you have a p of xi, you can take the log of p of xi, you can sum up the logs of the p of xi's. And so Shannon's entropy has the nice property of always being defined on a probability space. I should say, again, as an aside, that the sample space we're looking at here is finite, x1 to xn. In the usual way with probability spaces, you can go to infinite without too much damage, provided that you're careful that all the required sums or series converge. But the changing to continuous, again, as is often the case with probability theory, changing from the discrete case to the continuous case is a much bigger deal. And we'll say something about that later on in this section of our unit. So some more nice properties. It's always positive. This is straightforward enough. Probabilities lie between 0 and 1. The logs of number between 0 and 1 are non-positive. And so minus, and there's a minus there, minus the log of a probability is going to be a positive number. The probability itself is a positive number, and so h of x is greater than or equal to 0. In fact, we can see when it is equal to 0, and that's for a probability distribution where the probability of all the outcomes apart from one outcome is 0, and that outcome necessarily has probability 1. This is the case where the probability distribution isn't modeling something random, it's modeling something determined, because you already know what the outcome is going to be. Now, in this case, most of the p log p's are 0. We said before that p log p for p equals to 0 is 0. And the other one, the outcome that is probability 1, well, then you have 1 log 1, and the log of 1 is 0, and so that's 0 as well. So in the case where the distribution isn't really modeling something random, then you have Shannon's entropy 0. The other extreme is the case where all the outcomes are equally likely. So here, little n is the size of the sample space. It's the number of possible outcomes, x1 up to xn, and they're all equally likely. And so the probability for all x sub I is 1 over n. The log of 1 over n is minus the log of n, and so h of x, when you sum them all up, is going to be the log 2 of n. So now we have two examples: the determined case, where you have h of x is 0, the completely random case, where everything is equally likely. You have h of x is equal to the log 2 of n. And so, in fact, it turns out that these are bounds. This isn't difficult to prove. We're just not going to prove it here for the sake of time and space. I do urge you to look at the great book on information theory called Cover and Thomas, with references given on the website. Cover and Thomas goes through all these proofs. They're often quite elegant and delicate. This one isn't hard, but it is important to know that h of x lies between these two bounds, and not only that, but those bounds are only obtained in the examples we discussed. So h of x is bound by 0 and the log to the base 2 of the size of the sample space, and it is only 0 if one of the probabilities is 1, and hence all the others is 0, and it's only log to the base 2 of n if all the outcomes are equally likely. And so that kind of fits in with what we wanted for the entropy. The most entropic case, the case where we know least about the outcome of the experiment before we're told the outcome of the experiment, or to put it in terms of communication theory, the case where we know the least about what we'll learn from the channel before we consult what the channel tells us. That's the case where the outcome is truly random. That should be the case with the most entropy, and what we're telling you here that it is. Conversely, if we already know what the channel is going to tell us before we consult it, in other words, if the outcome is determined, then we gain no information from looking at the channel, and the entropy is indeed 0. So that's and everything else comes in between. That's exactly what we want. Let's look at the simplest cases, which is where n is equal to 2. So there's two outcomes. One outcome A, which is probability we'll call little p, and the other outcome B, which by the laws governing probabilities has to have probability 1 minus p. And so the entropy is going to be minus p log to the base 2 of p, minus 1 minus p log to the base 2 of 1 minus p, which isn't particularly nice. It's not a formula that simplifies it all, because formulas involving the sums and weighted sums of different logs very often don't. But we can plot it, and this is what it looks like here. You can see it's symmetric, as you'd hope. Being able to determine, knowing more about A and less about B, or more about B and less about A, it shouldn't be any different. and we can see that it's symmetric. You can do a change of formula in the change of the formula and see it's symmetric too. But what you can see is that it rises towards 1, logical space 2 of 2, in the middle when the two outcomes are equally probable, and falls progressively towards 0 in the two extremes, where p is equal to 0, in which case we know we're going to get b, or p is equal to 1, in which case we know we're going to get a. The real clincher, I guess, in convincing ourselves that Shannon's entropy does what it is we want it to do, evaluates the amount of information in a signal. The clincher, as far as that's concerned, is the source coding theorem. Again, we're not going to be able to derive or prove the source coding theorem here, but I just wanted to give you some idea about what it says. So consider a very simple case. We have a sequence of letters, and the letters take one of 4 values, A, B, C, or D. And so the sequence would look like, for example, A, B, A, C, B, D, A, D, D, A, B, C, D, A, B, D, A, etc. And so we have this long sequence of letters, and we want to digitize them or binarize them and communicate to somebody else what the sequence was. So we want to use a code, sequence of zeros and ones, to communicate the list of letters that we got. So we've got some, processes producing a list of letters chosen from A, B, C, and D. One example given is that they are the results of some sort of competition, people playing hands of cards or whatever, and you want to communicate to somebody else what's happening in the series of games. It doesn't matter, obviously. What we have is a sequence of A, B, C's, and D's, and we want to communicate that sequence to somebody else using zeros and ones. And so the obvious thing is just to write down the code. A corresponds to 0, 0, B corresponds to 0, 1, C corresponds to 1, 0, D corresponds to 1, 1. And so the code I had before becomes 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 1, 1. Take the binary solo. So obviously, if you receive this code, you know that they come in blocks of 2. So the first 2 must be A. The next 2 are 2 zeros again. That must be A again. The next 2 is a 0 and 1. That's B. The next 2 are an A, etc. And so once we receive the zeros and ones, we can get back to the sequence. One thing that you note is that the average length per letter, or the average number of bits per letter, is 2. That has to be the case because, in fact, the number of bits for each letter is 2. And so the sequences of zeros and ones is just twice the length of the list of A, B, C's, and D's. Now, the question is that the best code? And from where we are now, yes, it is. But imagine you had a little bit more information. Imagine you knew that A occurred 0.5 of the time, and B occurred 0.25 of the time, and C and D occurred the remaining 1/8 and 1/8 of the time. In other words, this sequence of A, B, C's, and D's isn't completely random. A occurs more often than B, which occurs more often than C and D. If you have this extra information, can you come up with a shorter code? And the answer, it turns out, is yes. So can we use this information to make the average length of the code, the average number of bits per letter, shorter? And well, the answer is yes. The regularity, the predictability of the sequence allows the code to be compressed. So here's a fancy code, a better code. A is 0, B is 1, 0, C and D are 1, 1, 0 and 1, 1, 1. You can see that this is a good idea because A is the most frequent letter, and so you would like to use a shorter code word for it. So before A had 2 bits associated with, now it only has 1 bit. B was 2 bits before, still 2 bits, and unfortunately, in order to achieve this, C and D have to be 3 bits. You might say, well, why not just make one of them 1, 1, and then you'll have another code word that's only 2 bits, or why not just use A as 0 and B as 1? Well, the answer there, of course, is that you can't segregate the code So this is a clever code in that it's a prefix-free code. What that means is that no code word is the start of another code word. So A is 0, and none of the other code words start with 0. And B is 1, 0, and none of the other code words start with 1, 0. Which means when you write the code down for the sequence, A, B, A, C, D, well, the first 0, that can't be the prefix of another code word. So you know that must be a coding for something, and from your code book you can see it codes for A. The same for this A. Now the 1, 0, when you get to the 1, well, you don't know what one's code. Well, one's not, just looking at the 1, you don't know what it's coding for, because 1 isn't a complete code word from your dictionary. But when you look at the next digit, it's 0, and so that you know that you must have to stop there, because none of the other code words start with 0. Similarly with the 0, that's an A. The 1, 1, well, once you've done 1, 1, you don't know where you are, so you have to add the next bit, but then that's 0, and then again with the D. And so this code, it is possible to split the sequence of zeros and ones into the individual code words for the A, B, C, and D. As I said, it's a prefix free code. Obviously, there's a problem here. If there's some ambiguity as to where the sequence starts, you're in trouble. If you had the third digit of C, that's a 0. And so if you started there thinking that was the start, then you think that was an A. And so that would cause a problem. That's a similar problem, actually, that the original binary coding with the 0, 0, 1, 0, etc. had as well. If you don't know where the start point is, then you'll get the wrong decoding. You cannot come up with these codes where you can resolve that ambiguity, but that's a whole separate subject. But a whole extra thing. Here, the point is that we now have this new code where we've managed to give a shorter code word. And has that worked? Well, indeed it has. So if we look here, the length is, well, the probability of A is 0.5 and it's 1 bit long. So this is the expected length per letter that we're coding for. So for the A's, it's 1, the length of the code word for A, multiplied by 0.5, the probability of A. For B, it's 0.25, the probability of B, by 2, the number of the length of the code word for B. For C and D, then it's 0.125, their probabilities, multiplied by 3, the number of bits, and then we get 1.75. And the point is that 1.75 is smaller than 2. And so we've actually come up with a more efficient code. Or another way of putting it is that we've compressed the code. And so before, when we just had A, B, C, and D, we didn't know anything else about them, or say they were equally probable, there was no way of compressing it, because that all we could do was code for whichever letter was being sent. But here, we know a little bit more. We know something about the regularity. We know something about the distribution of A, B, C, and D. And that's allowed us to compress the data and give us a shorter code, a more efficient code. But you'll notice that that's the same as Shannon's entropy. So here we have Shannon's entropy, h of x. H of x is equal to minus 0.5 by the log to the base 2 of 0.5, which of course is 1, and then minus 0.25 by the log minus the log to, we have 0.25 by minus the log to the base 2 of 0.25, and minus the log to the base 2 of 0.25 is 2, and then twice, giving us 0.25, we have minus the log to the base 2 of 0.125, and the log to the base 2 of 0.125 is minus 3. And so each of these logs is giving us the length of the corresponding code word. And because of that, the Shannon's entropy is also equal to 1.75. And so you'll notice that the Shannon's entropy for the code is the same as the expected length. That is kind of special. So you'll see that A was probability 0.5 and B was probability 0.25. But say A had probability 0.55, then the log to the base 2 of 0.55 wouldn't give us an integer. And so obviously that couldn't correspond to the length of the code word coding for A. it was only because I chose A, B, C, and D to be these powers of a half that this thing worked out exactly, that h of x was equal to 1.75. But the source coding theorem tells us that that's just a rounding error, that the length of the most efficient code, given that you know the probability distribution of the letters you're coding for, is greater than or equal to the entropy of that distribution and less than the entropy plus 1. In other words, because code words have to have an integer length, the logs and the corresponding code word lengths can't be the same. But as I said, it's just a rounding error. The source coding theorem says that if you have a sequence of objects and they have some regularity and you want to code them in a binary code, the length of that binary code has a fundamental lower bound, which is the Shannon's entropy, and that you can actually obtain a code that is within one of the Shannon entropy. And what you're really saying is that you can find a way of distributing the lengths of the code words while still producing prefix-free codes, so that the log p is nearly equal to or equal to the length of the code word. So if you look, you see we had the log to the base 2 of 0.5 is 1, and when we came up with our code, we had a code word for A that was length 1. Similarly, the code word for B was length 2, and in the calculation of Shannon's entropy, the B contributes a log of 0.25, which is equal to -2. And so what this is saying, what the source coding theorem is saying, is that it's possible to find a prefix-free code so that the log of the probability is close to the length of the code word for that outcome. When Shannon proved his theorem, he proved that this could be done, but it wasn't known at the time how it was done. That was discovered by someone called Huffman. These particular codes are called Huffman codes. So basically, the source coding theorem shows that the entropy h of x is a lower bound on the average length of the message using the most efficient code. And so it's the number of bits used to describe the outcome, given that you know something about how expected or unexpected each of the outcomes are. So it's the Shannon's entropy is a limit on the compression of the information, and so it's a good measure of that information. Thank you.